Tonight, we're going to leave. Not in any ordinary sense, not by boarding something or traveling somewhere physical. Tonight, you will simply lie still, let your breathing slow, and follow a journey that begins at your feet and extends outward further than any spacecraft humanity has ever sent. We are going to travel from here, from the surface of the Earth, out to the edge of the solar system. And along the way, we will visit every world our sun claims as its own. Every ring and moon and cloud of ice and ancient frozen rock. Every known boundary and uncertain threshold. Every place humanity has reached and every place we can only theorize about. This is not a quick journey. The solar system is not a small place. If there is one thing tonight will give you, before sleep finds you, it is a new appreciation for the size of the space in which we live. You know the solar system exists. By the time this journey ends, you will feel it. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The first thing to understand about the solar system is that no map has ever captured it, honestly. Every diagram you have ever seen in a textbook, in a classroom, on a poster, has cheated. The diagrams have to cheat. The distances involved are so enormous that any accurate diagram drawn at a scale where the planets were large enough to see would require a piece of paper several kilometers long, possibly longer. Let's start with the number that anchors everything else, the distance from the Earth to the Sun. It is approximately 150 million kilometers. Astronomers call this distance 1 astronomical unit. 1 astronomical unit. And they use it as the measuring stick for everything in the solar system. When we say Jupiter is 5.2 astronomical units from the Sun, we mean it is 5.2 times further from the Sun than the Earth is. 150 million kilometers. Let's try to make that real. Light travels at 299,792 kilometers per second. At that speed, a photon of light leaving the surface of the Sun takes approximately 8 minutes and 20 seconds to reach the Earth. You have probably heard this before, but consider what it means. The Sun you see in the sky is not the Sun as it is right now. It is the Sun as it was 8 minutes and 20 seconds ago. You are always looking slightly into the past. When you look at the Sun, you are looking backward in time by 8 minutes. When you look at the nearest star beyond our Sun, you are looking backward in time by 4 years. When you look at distant galaxies, you are looking backward by billions of years. The night sky is not a snapshot of now. It is an archive. If you were to drive to the Sun, assuming you could, and that the car was somehow impervious to heat, at a constant 100 kilometers per hour, the journey would take approximately 171 years, non-stop, 24 hours a day, for 171 years. You would need to have set out around 1854 to arrive today. If you walked at a brisk 5 kilometers per hour, the journey would take roughly 3,400 years. You would need to have departed around 1375 BCE, before the fall of Troy, to arrive this evening. Now, hold that number, 150 million kilometers, 1 astronomical unit, 8 minutes at the speed of light, and consider that the edge of the solar system, where the Sun's influence finally surrenders to the interstellar void, is not one astronomical unit away. The boundary where the Sun's solar wind finally gives out, the heliopause, sits at approximately 120 astronomical units. And even that is not the true edge. The Oort cloud, the vast shell of frozen debris that marks the outermost structure of the solar system, extends to perhaps 100,000 astronomical units from the Sun. That is 100,000 times the Earth-Sun distance. At 100 kilometers per hour, the drive to the inner edge of the Oort cloud, at roughly 2,000 astronomical units, would take approximately 342,000 years. To the outer edge of the Oort cloud at 100,000 astronomical units, the drive would take approximately 17 billion years. Slightly longer than the age of the universe, this is the solar system we are about to travel through. The spacecraft humanity has sent furthest is Voyager 1. Launched in 1977, now more than 45 years into its journey and still transmitting data back to Earth, Voyager 1 is currently around 163 astronomical units from the Sun. It crossed the heliopause, the boundary of the heliosphere, the bubble of solar wind around our Sun, in 2012, becoming the first human-made object to enter interstellar space. At the speed Voyager 1 travels, roughly 17 kilometers per second, it would take approximately 300 years to reach the inner Oort cloud. It would take roughly 30,000 years to cross through the Oort cloud entirely. We have sent one small spacecraft barely past the front door. Tonight, we will travel all the way to the edge. We begin on Earth, standing on solid ground under the same sun that has been rising and setting over this planet for approximately 4.6 billion years. The Earth is not a large planet. With a radius of approximately 6,371 kilometers, it is the fifth largest planet in the solar system, which is a misleading statistic because the fifth largest is quite small compared to what lies further out. Everything about the scale of the solar system is like this, a constant revision of what you thought you understood. Earth sits at 1 astronomical unit from the Sun. It takes 365.25 days to complete one orbit. Its axial tilt of 23.5 degrees is why we have seasons. Its single large moon with a radius of 1,737 kilometers sits approximately 384,400 kilometers away. A distance light covers in about 1.3 seconds. The Moon formed approximately 4.5 billion years ago, almost certainly from the debris of a collision between the early Earth and a Mars-sized body called Theia. It is slowly moving away from us at a rate of about 3.8 centimeters per year. In a billion years or so, it will be far enough away that total solar eclipses, as we know them, will no longer be possible. Moving inward from Earth toward the Sun, we encounter two planets before reaching the solar boundary. Venus, at 0.72 astronomical units, is often called Earth's twin. The two planets are nearly identical in size. Venus has a radius of 6,051 kilometers compared to Earth's 6,371. They formed from the same primordial cloud of gas and dust at roughly the same time, and yet they could not be more different. Venus is a catastrophe. Its atmosphere is 96% carbon dioxide, 90 times denser than Earth's, the equivalent in terms of pressure on the surface of being 900 meters underwater. The surface temperature is approximately 465 degrees Celsius, hot enough to melt lead. Hot enough that spacecraft landing on Venus have historically survived only a matter of hours before being destroyed. The reason Venus is so hot has nothing to do with its proximity to the Sun and everything to do with what its atmosphere does with the Sun's energy. The dense carbon dioxide layer traps heat extraordinarily effectively. Venus has undergone a runaway greenhouse effect, a state in which warming causes more water vapor in the atmosphere, which causes more warming, which causes more evaporation, until the process becomes self-reinforcing and irreversible. Every drop of liquid water on Venus evaporated long ago. Its days are strange as well. Venus rotates so slowly that a single Venusian day, one full rotation on its axis, takes 243 Earth days, longer than a Venusian year, which takes only 225 days, and it rotates backwards. If you stood on the surface of Venus, the Sun would rise in the west and set in the east. Mercury, at 0.39 astronomical units, is the innermost planet and the smallest. Its radius is just 2,439 kilometers, smaller than several moons elsewhere in the solar system. Without a substantial atmosphere to distribute or retain heat, Mercury has the most extreme temperature variation of any planet. Surface temperatures swing from approximately 430 degrees Celsius in full sun to negative 180 degrees in permanent shadow. Mercury is heavily cratered, ancient-looking, bearing the marks of a period in the early solar system called the Late Heavy Bombardment, roughly between 4.1 and 3.8 billion years ago, when an enormous number of asteroids and comets were flung through the inner solar system. The scars are still visible because Mercury has almost no geological activity to resurface it, no weather to erode the craters away. What you see on Mercury's surface is essentially a record of 4 billion years of impacts, preserved almost perfectly. Now, we turn outward. Earth behind us, we head toward the outer solar system. Mars sits at 1.52 astronomical units. It is roughly half the diameter of Earth, with a radius of 3,390 kilometers. Its thin atmosphere, mostly carbon dioxide, but only 1% as dense as Earth's, provides almost no protection from radiation and almost no heat retention. Average surface temperatures are around negative 60 degrees Celsius, though they swing from about 20 degrees near the equator in summer to negative 125 degrees at the poles in winter. Mars has the largest volcano in the solar system, Olympus Mons, which rises approximately 21.9 kilometers above the surrounding plain. It also has the longest canyon system, Valles Marineris, which stretches approximately 4,000 kilometers across the Martian surface, roughly the width of the United States. For reference, the Grand Canyon is about 446 kilometers long. Valles Marineris is nearly 10 times longer and vastly deeper, reaching depths of around 7 kilometers in places. Mars has two small moons, Phobos and Deimos, that are almost certainly captured asteroids. Phobos orbits so close to Mars that it completes 3 orbits per Martian day, rising in the west and setting in the east. It is also gradually spiraling inward. In roughly 50 million years, Phobos will either crash into Mars or be torn apart by tidal forces to form a ring. The surface of Mars is red because of iron oxide, rust in the soil and dust. The sky on Mars is not blue. It is a pale butterscotch, reddish during dust storms. Sunsets on Mars are blue, the reverse of Earth, because fine dust particles scatter red and yellow light while allowing blue light to pass through. The effect is strange and beautiful. We have photographed it. We know more about the surface of Mars than we do about the surface of our own ocean floor. Dozens of spacecraft have visited it. Rovers have driven across it. We have analyzed its rocks, photographed its moons, and in 2021 successfully flew a helicopter in its thin atmosphere. The helicopter, Ingenuity, was designed for 5 flights. It completed 72 before finally being grounded by rotor damage in January 2024. It outlived its planned mission by years. The question of whether Mars once had liquid water on its surface, and therefore possibly life, is one of the most actively investigated questions in planetary science. The current evidence strongly suggests Mars was once warmer, wetter, and substantially different. Ancient river valleys, delta formations, and mineral deposits that form only in the presence of water have all been identified. Whatever Mars was once, it is very different now. We cross Mars's orbit and continue outward. Ahead lies a transition zone between the rocky, terrestrial planets of the inner solar system and the gas giants of the outer, a region that tells a story about the early chaos of the solar system. Between roughly 2.2 and 3.2 astronomical units from the Sun, in the gap between Mars and Jupiter, lies the asteroid belt. The name suggests something dense and dangerous, the kind of narrow corridor of tumbling boulders depicted in science fiction, through which spacecraft must thread carefully, narrowly avoiding collisions every few seconds. The reality is almost comically different. The asteroid belt is enormous and almost completely empty. It contains hundreds of thousands of objects larger than 1 kilometer in diameter and millions more below that size. But spread across the vast volume of space between 2.2 and 3.2 astronomical units, the density of matter is extraordinarily low. The average distance between asteroids is approximately 600,000 kilometers. Every spacecraft we have ever sent through the asteroid belt has passed through without incident. The probability of a spacecraft randomly encountering an asteroid on a direct trajectory is vanishingly small. The total mass of the entire asteroid belt is approximately 4% of the mass of the Moon. It is mostly empty space containing scattered rocky debris. The story of why this debris never coalesced into a planet is a story about Jupiter. Jupiter's gravitational influence is so powerful that during the formation of the solar system, it repeatedly disrupted any attempt by material in this region to collect into a planet. Every time gravity began pulling material together, Jupiter's pull stretched and distorted the growing body, breaking it apart. Over millions of years, much of the original material in this region was ejected from the solar system, sent crashing into the inner planets, or lost to other dynamics. What remains today is a tiny fraction of what was once there, the leftover rubble of a planet that never formed. The 4 largest objects in the asteroid belt are Ceres, Vesta, Pallas, and Hygeia. Between them, they account for more than half the total mass of the belt. Ceres, the largest, has a diameter of approximately 940 kilometers and was classified as a dwarf planet in 2006, the same year Pluto was reclassified. The Dawn spacecraft visited Ceres in 2015 and revealed a heavily cratered surface with mysterious bright spots that turned out to be deposits of sodium carbonate, salts exposed at the surface, possibly left behind when subsurface water ice reached the surface and sublimated. Ceres may have a layer of liquid water beneath its icy mantle. Vesta, the second largest, is distinctive for having a different origin story. It has a large iron core, suggesting it underwent a process called differentiation. It grew large enough in the early solar system for its interior to separate into layers, with heavy metals sinking toward the center and lighter materials rising to the surface. Vesta is essentially a protoplanet, a body that was on its way to becoming a planet before Jupiter disrupted the process. The asteroid families we see in the belt today, groups of asteroids with similar orbital characteristics and compositions, are in many cases the fragments of larger bodies that were shattered by collisions long ago. The asteroid belt also contains Trojan asteroids, objects that share Jupiter's orbit, sitting at gravitational equilibrium points 60 degrees ahead of and behind Jupiter in its path around the Sun. These positions, called Lagrange points, are natural gravitational traps. Jupiter's Trojans number more than 1 million objects larger than a kilometer. They have been there, essentially undisturbed, for billions of years. The asteroid belt was the first major barrier crossed by the Pioneer 10 spacecraft in 1972, the first human-made object to travel through it. The mission scientists were genuinely uncertain whether the spacecraft would survive the transit. It passed through completely unaffected. We pass through the belt and continue outward. At 3.2 astronomical units, we leave the last of the rocky debris behind. The temperature drops. The sunlight grows dimmer. And then, slowly, something begins to dominate the sky ahead. Something at 5.2 astronomical units that begins to make everything else feel small. At 5.2 astronomical units from the Sun, Jupiter announces itself long before you arrive. It doesn't present itself gradually. It dominates. Its gravitational influence reaches across hundreds of millions of kilometers. Its magnetic field extends so far in the direction away from the Sun that its magnetospheric tail stretches past the orbit of Saturn. It has 95 confirmed moons. It is, in every sense, the dominant presence in the outer solar system, and arguably the dominant presence in the entire solar system after the Sun itself. Jupiter is what astronomers call a gas giant. It has no solid surface. If you descended into Jupiter's atmosphere, there is no ground to reach. You would enter the upper clouds and simply sink, the pressure and temperature rising around you. The atmosphere is approximately 90% hydrogen and 10% helium, with trace amounts of methane, water vapor, ammonia, and other compounds. As you descended, the hydrogen would gradually change its state from gas to liquid to, deep enough, a form of matter that doesn't exist naturally anywhere on Earth, metallic hydrogen. Under pressures of roughly 2 million atmospheres, hydrogen loses its electrons and behaves like a liquid metal. This metallic hydrogen layer rotating with the planet is believed to generate Jupiter's extraordinary magnetic field, by far the strongest of any planet in the solar system. Jupiter's magnetic field at the equator is approximately 14 times stronger than Earth's. Jupiter is large, absurdly large. It has a diameter of approximately 139,820 kilometers, about 11 times the diameter of Earth. If the Earth were the size of a grape, Jupiter would be the size of a basketball. Its volume is more than 1,300 times that of Earth. You could fit every other planet in the solar system inside Jupiter and still have room. Its mass is 300 18 times that of Earth. It is 2.5 times more massive than all the other planets combined. Despite this mass, Jupiter rotates faster than any other planet. Its day lasts approximately 10 hours. For an object that large spinning that quickly, the result is a noticeable equatorial bulge. Jupiter is measurably wider at the equator than at the poles. That rapid rotation also drives its weather. The banded appearance of Jupiter, alternating light and dark stripes visible even through a modest amateur telescope, is the result of atmospheric circulation. The lighter bands are zones where gas rises. The darker bands are belts where gas sinks. These features evolve, shift, and change over months and years, driven by the enormous energy Jupiter radiates from its interior. Jupiter releases approximately 1.7 times more heat than it receives from the Sun. The remnant heat of its formation still slowly leaking out after 4.5 billion years. The most famous feature of Jupiter's atmosphere is the Great Red Spot. It is a storm, specifically an anticyclonic storm, a high-pressure system rotating counterclockwise that has been observed continuously since the 1600s. Astronomers first recorded it as a permanent feature in 1665. It has been raging for at least 350 years through the entire period of modern science, through every war and revolution and discovery in that time, through the Industrial Revolution and the space age and the invention of computing and the mapping of the human genome. While all of that was happening, this storm was turning. At its current size, the Great Red Spot is approximately 16,000 kilometers wide. That number sounds impressive until you consider it was once much larger. Historical observations suggest it was roughly twice its current size in the 19th century. It is shrinking. Current models suggest it may disappear entirely sometime in the next few decades. When it does, a storm that has outlasted every human civilization born since the Renaissance will simply end. The Galilean moons are 4 large moons discovered by Galileo Galilei in January 1610. They were among the first objects in the solar system observed through a telescope, and Galileo's observation of them orbiting Jupiter rather than Earth was an early piece of evidence for the heliocentric model of the solar system. That observation in 1610 helped begin the unraveling of a cosmology that had been accepted for over 1,000 years. Io, the innermost Galilean moon, is the most volcanically active body in the solar system. It is caught in a gravitational tug-of-war between Jupiter and the other large moons, and this gravitational flexing generates enormous heat through a process called tidal heating. The result is a surface covered in hundreds of active volcanoes, erupting sulfur and sulfur dioxide in plumes that can reach heights of 500 kilometers. The surface of Io is constantly being resurfaced by this activity. There are almost no impact craters because the surface is renewed too quickly for craters to persist. Io's colors, yellow, orange, red, white, black, come from the different sulfur compounds deposited by different eruptions. It looks like a pizza, which is what mission scientists called it when Voyager 1 first sent back images in 1979. Europa, the second Galilean moon, may be the most important body in the solar system when it comes to the question of life beyond Earth. Beneath its smooth, icy surface, Europa is believed to harbor a global liquid water ocean. This ocean is not directly observable, but the evidence is compelling. The surface is covered in a network of cracks and ridges consistent with movement in the ice. There is a weak magnetic field that fluctuates in a way suggesting a conducting layer beneath the surface, and tidal heating provides an energy source. The ocean below Europa's ice is thought to contain more liquid water than all of Earth's oceans combined. Liquid water, a heat source, evidence of the chemical compounds necessary for biochemistry. The conditions we associate with life on Earth appear to be present below the ice, on a moon 628 million kilometers from the Sun. NASA's Europa Clipper spacecraft, launched in October 2024, is on its way to Jupiter and will arrive in 2030. It will make dozens of close flybys of Europa, gathering data on the ocean, the ice shell, and the chemical environment. Ganymede is the largest moon in the solar system. It is larger than the planet Mercury, with a diameter of 5,268 kilometers. It is the only moon known to generate its own magnetic field internally. Like Europa, it likely has a subsurface liquid water ocean, possibly even larger. Callisto, the outermost of the 4 Galilean moons, is the most heavily cratered object in the solar system. Its surface has had almost no geological activity since the early solar system. Every crater that formed is still visible, essentially perfectly preserved. Callisto is a record of approximately 4 billion years of bombardment. We pass through Jupiter's system and continue outward. The Sun is now 5 times dimmer than from Earth. The temperature of space, already cold, falls further. And ahead, still enormous, even at this distance, is the most visually striking planet in the solar system. At 9.5 astronomical units, Saturn. There is no other object in the solar system quite like it. You have seen pictures, the planet with the rings. You may have seen it through a telescope. The moment an amateur astronomer points their instrument at Saturn for the first time and actually sees it, the disk, the rings, clearly separate, clearly real. People who see Saturn through a telescope for the first time often don't believe they're seeing the actual planet. It looks too perfect, too much like an illustration. But it is real, and it is extraordinary. Saturn is a gas giant like Jupiter, but slightly smaller. Its diameter is approximately 116,460 kilometers, about 9.5 times that of Earth. Its mass is 95 times Earth's. Like Jupiter, it has no solid surface, is primarily hydrogen and helium, and has bands and storms, though generally less dramatic than Jupiter's. Saturn radiates more energy than it receives from the Sun, roughly 2.5 times as much, driven partly by a process in which helium gradually rains downward through the hydrogen interior, releasing gravitational energy as heat. Saturn rotates quickly. Its day is approximately 10.7 hours. It is also the least dense planet in the solar system, less dense than water. If you could find an ocean large enough, Saturn would float. This low density and rapid rotation give it a noticeably oblate shape, significantly wider at the equator than at the poles. But the rings. Saturn's ring system extends from approximately 7,000 kilometers above Saturn's equator to approximately 80,000 kilometers above it. The total diameter of the main ring system is roughly 282,000 kilometers. The moon's orbit around Earth would fit inside it. And yet, despite spanning this extraordinary distance, the rings are almost impossibly thin. The main rings are estimated to be between roughly 10 meters and 1 kilometer thick, depending on location. The ratio of their width to their thickness is comparable to a sheet of paper spread across a football field. The rings are composed primarily of water ice, particles ranging in size from tiny grains to chunks several meters across. They are bright because ice reflects sunlight well. The ring system is divided into distinct regions separated by gaps. The most prominent gap, the Cassini division, is approximately 4,800 kilometers wide and appears dark because it contains relatively little material. The division is the result of a gravitational resonance with Saturn's moon Mimas. Any particle in the Cassini division would complete exactly 2 orbits for every 1 orbit of Mimas, and this repeated gravitational nudge clears the region over time. The current leading hypothesis, supported by data from the Cassini spacecraft, is that Saturn's rings are relatively young, perhaps 10 to 100 million years old, a blink of an eye in solar system time. The most likely origin is the disruption of a former moon torn apart by tidal forces when it came too close to Saturn. The rings may be temporary. They are slowly losing material, eroding inward as ring particles rain down into Saturn's atmosphere. In another few 100 million years, the rings as we know them may be gone. We happen to exist at a rare moment in Saturn's history, the moment the rings are at their most spectacular. Saturn has 146 confirmed moons. The largest is Titan. Titan is remarkable. With a diameter of 5,150 kilometers, it is the second largest moon in the solar system. What makes it unique in the entire solar system is its atmosphere. Titan has a thick atmosphere denser than Earth's at the surface, composed primarily of nitrogen, with methane as the second largest component. This makes it the only world in the solar system besides Earth with a nitrogen-dominated atmosphere. Titan has a weather, not water weather, methane weather. Methane on Titan undergoes a cycle analogous to the water cycle on Earth. It evaporates from the surface, rises into the atmosphere, condenses into clouds, falls as rain, flows across the surface in rivers, and collects in lakes and seas at the poles. The Huygens probe, which descended through Titan's atmosphere in January 2005, the first landing ever achieved on a world in the outer solar system, revealed a landscape of mountains, river valleys, and dark plains of organic material. Subsequent Cassini observations revealed the methane lakes of Titan's polar regions, some of them larger than the Great Lakes of North America. The temperature on Titan's surface is approximately negative 179 degrees Celsius. At that temperature, methane is a liquid. Water is so cold it forms solid rock. The mountains on Titan are made of water ice. The rain falls gently because Titan's gravity is low and its atmosphere is thick. Rain drops fall at about 1.5 meters per second, rather than the several meters per second they reach on Earth. It rains slowly on Titan. Whether Titan could support any form of life is a question scientists take seriously. Not life as we know it. Life based on water chemistry would freeze solid at Titan's temperatures, but the possibility of different chemistry built around liquid methane rather than liquid water has been proposed. It is speculative. It is not dismissed. NASA's Dragonfly mission, a rotorcraft lander designed to fly between multiple locations on Titan's surface, was approved in 2019 and is currently planned for launch in the late 2020s, with an arrival at Titan around 2034. It will be the first mission to explore Titan's surface directly since Huygens, and the first to fly through another world's atmosphere. on powered flight. Enceladus, one of Saturn's smaller moons at approximately 504 kilometers in diameter, is white. Completely white, it is the most reflective body in the solar system, reflecting nearly 100% of the sunlight that hits it. The reason is that its surface is constantly being resurfaced by freshwater ice. During its 13-year mission in the Saturn system, the Cassini spacecraft discovered that Enceladus has geysers. From cracks near its south pole, named the Tiger Stripes, Enceladus erupts plumes of water vapor, ice particles, and organic compounds into space continuously. These plumes feed Saturn's E-ring, and they come from a liquid water ocean beneath the ice. Cassini flew directly through those plumes and measured their composition. It found water, carbon dioxide, methane, hydrogen, and a range of organic molecules. It found evidence of hydrothermal activity on the ocean floor, warm water meeting rock, precisely the environment where, on Earth, some of the most productive and extreme ecosystems exist, far from any sunlight. The hydrothermal vents of Earth's ocean floor support entire communities of life based not on photosynthesis, but on chemosynthesis, the chemical energy of the vent fluid. Enceladus appears to have those same conditions beneath its ice in the dark. Enceladus is now considered one of the best candidates in the solar system for finding life. Every observation we have made has confirmed, step by step, that the conditions necessary for life as we understand it appear to be present. A future mission specifically designed to sample the plumes of Enceladus and analyze them for biosignatures, chemical signs of life, is among the most compelling proposals in planetary science. We continue past Saturn deeper into the outer solar system. The Sun behind us is now a bright disk, but noticeably smaller than from Earth. The temperature continues to drop. We are moving into territory that Cassini never reached, that only the Voyager spacecraft passed through in the 1980s. The ice giants await. At 19.2 astronomical units, Uranus. In the public imagination, Uranus is perhaps the least romanticized of the outer planets. It lacks the colossal visual drama of Jupiter or the perfect ring system beauty of Saturn. It is a pale blue-green disk in telescopes, featureless to the casual observer, somewhat overlooked. This is an injustice. Uranus is one of the strangest planets in the solar system. Uranus is classified as an ice giant rather than a gas giant, a distinction that reflects its composition. Unlike Jupiter and Saturn, which are predominantly hydrogen and helium, Uranus contains a much higher proportion of ices, water, methane, and ammonia, mixed with hydrogen and helium. The blue-green color comes from methane in the upper atmosphere, which absorbs red light and reflects blue-green. Its diameter is approximately 50,724 kilometers, about 4 times that of Earth. Its mass is approximately 14.5 times Earth's. But the most remarkable thing about Uranus is its axial tilt. Every planet is tilted to some degree. Earth is tilted at 23.5 degrees relative to its orbital plane. That tilt gives us seasons. Mars is tilted similarly at about 25 degrees. But Uranus is tilted at 97.8 degrees. It is essentially lying on its side. Its poles point almost directly toward and away from the Sun, rather than roughly perpendicular to its orbit. What this means in practice is strange to contemplate. At the poles of Uranus, the Sun does not rise and set each day. Instead, One pole faces the sun continuously for 42 years, a Uranian summer, while the other pole faces away in continuous darkness for 42 years of winter. Then the planet completes its orbit, and the situation reverses. At the equinoxes, when the sun is directly over Uranus's equator, you would see something more familiar. A sun rising and setting each day. But at the extreme of summer or winter, a person standing at one of the poles would watch the sun spiral slowly overhead for decades, never setting as Uranus carried them through its long orbit. The cause of this extreme tilt is almost certainly a massive impact in the early solar system. Something very large struck Uranus and effectively knocked it over. We don't know exactly what. The evidence is entirely in the tilt itself and in the fact that Uranus's moons orbit around its tilted equator, consistent with forming from debris after such an impact. Whatever struck Uranus was probably roughly Earth-sized. Uranus has 28 known moons, all named after characters from the works of William Shakespeare and Alexander Pope, an unusual convention for the solar system, where most moons carry names from Greek and Roman mythology. Miranda, at just 471 kilometers in diameter, has a surface that contains one of the most dramatic landscapes in the solar system. A cliff called Verona Rupes that drops approximately 20 kilometers straight down. It is the tallest known cliff in the solar system. If you fell off Verona Rupes, in Miranda's weak gravity, the fall would take roughly 12 minutes. Uranus has a ring system discovered in 1977. The rings are narrow, dark, and largely composed of organic compounds, quite different from Saturn's bright ice rings. They are much less spectacular visually, but they are there. One puzzling thing about Uranus is how little internal heat it radiates. Jupiter radiates 1.7 times more energy than it receives from the Sun. Saturn radiates 2.5 times more. Uranus radiates approximately the same amount as it receives, no measurable excess. This is deeply unusual and not fully explained. Something about Uranus's interior appears to prevent the heat of its formation from leaking out. It may have an internal layer that acts as a thermal blanket, trapping heat far below the observable outer atmosphere. We have visited Uranus once with any spacecraft. Voyager 2 flew past in January 1986, spending approximately 6 hours in the vicinity of Uranus before continuing outward. That flyby revealed the rings, the moons, the atmosphere, the magnetic field. The magnetic field is peculiar. It is tilted 59 degrees from the rotation axis, and unlike most planetary magnetic fields, it does not pass through the center of the planet. It is offset from the center by roughly 1/3 of the planet's radius. No one fully understands why. Everything we know about Uranus at close range comes from those 6 hours in January 1986. We have not been back. A proposed future mission, the Uranus Orbiter and Probe, was identified in 2022 as the highest priority large flagship mission for planetary science in the coming decade. If funded and developed on schedule, it could arrive at Uranus in the early 2040s. We may spend decades before we look at this world properly, from close range, for the first time. We continue outward. Uranus falls behind. The Sun is now 19 times dimmer than it appears from Earth. We are approaching the last planet. At 30.1 astronomical units, Neptune. Neptune is the furthest planet from the Sun. It is cold, dark, and impossibly far from any warmth by any human intuition. Sunlight at Neptune's distance is approximately 900 times dimmer than at Earth. The Sun, viewed from Neptune, appears as an extremely bright star, visible to the naked eye, clearly brighter than anything else in the sky, but not a disk, just the brightest star. Neptune is also an ice giant like Uranus, similarly dominated by water, methane, and ammonia ices. Its diameter is approximately 49,244 kilometers. Its mass is approximately 17 times Earth's, slightly more massive than Uranus despite being almost the same size. But Neptune, unlike Uranus, is active. Neptune has the fastest recorded wind speeds of any planet in the solar system. Winds in Neptune's atmosphere have been measured at up to 2,100 kilometers per hour. On Earth, a Category 5 hurricane has winds above 252 kilometers per hour. Neptune's winds are roughly 8 times faster. The energy driving these winds, given how little solar energy reaches Neptune, must come from the planet's interior. Neptune radiates approximately 2.6 times more energy than it receives from the Sun. Neptune is intensely blue, deeper blue than Uranus's blue-green. The color comes from atmospheric methane, but the precise depth of blue suggests some additional absorbing compound in the atmosphere that hasn't been fully identified. Like Jupiter, Neptune has had observed storm systems. In 1989, Voyager 2 discovered what it named the Great Dark Spot, a storm system comparable in relative size to Jupiter's Great Red Spot. When Hubble observed Neptune in 1994, the Great Dark Spot was gone. A new dark spot had appeared elsewhere. Neptune's storms appear more transient than Jupiter's. They form and dissipate over years rather than centuries. Neptune has 16 known moons. The most significant is Triton. Triton is unusual in almost every way. With a diameter of approximately 2,706 kilometers, it is the 7th largest moon in the solar system. It has a thin nitrogen atmosphere and an extraordinary surface, mostly frozen nitrogen ice, with a south polar cap that appears pink-tinged from tholins, those complex organic compounds we have now encountered on several outer solar system bodies. Triton has geysers. From its south polar region, eruptions of nitrogen gas rise several kilometers into the thin atmosphere, driven by a subtle sublimation mechanism in which even the faint sunlight at this distance is enough to heat subsurface ice until it vaporizes. The gas escapes through cracks and is blown downwind, leaving dark streaks on the surface visible in Voyager 2 images. But the strangest thing about Triton is its orbit. It orbits Neptune backwards. Every major moon in the solar system orbits its planet in the same direction the planet rotates, a natural consequence of forming from the same rotating disk of material. Triton orbits in the opposite direction. This retrograde orbit is unmistakable evidence that Triton did not form around Neptune. It was captured from elsewhere. Triton was once a Kuiper belt object, a body from the region of space we are about to enter, that wandered too close to Neptune and was caught by its gravity. The consequences of that capture are still unfolding on a very long time scale. Tidal forces are slowly decelerating Triton, causing it to spiral gradually inward. In approximately 3.6 billion years, Triton will cross Neptune's Roche limit, the distance within which tidal forces would overcome Triton's own gravity and tear it apart. When that happens, Triton will become a ring. Neptune will briefly have a spectacular ring system, then the material will disperse. Neptune's future is, in this sense, already written. We have visited Neptune once, Voyager 2 after flying past Jupiter in 1979, Saturn in 1981, and Uranus in 1986, reached Neptune in August 1989. It spent approximately 5 hours in close proximity to Neptune and Triton before continuing its journey out of the solar system. Everything we knew about Neptune at close range for the next several decades came from those 5 hours. In 2023, the James Webb Space Telescope turned its gaze on Neptune and produced images of extraordinary clarity, the sharpest view of Neptune's rings since the Voyager 2 flyby, along with detailed atmospheric data. Webb was not built to study Neptune. It is designed for deep observations of the distant universe, but its sensitivity is so extreme that it can observe the outer planets with remarkable detail from Earth orbit. We pass Neptune. We have passed the last planet. We are 30 astronomical units from the Sun. Ahead, the solar system does not end, it continues, but it changes. What lies ahead is not empty void. It is something older and stranger than the planets we have just left behind. Beyond Neptune's orbit begins a region called the Kuiper Belt. It extends from approximately 30 astronomical units, where Neptune's orbit ends, out to roughly 50 astronomical units from the Sun. The Kuiper Belt is often compared to the asteroid belt, but this comparison undersells it considerably. The Kuiper Belt is roughly 20 times wider than the asteroid belt and 20 to 200 times more massive. It contains hundreds of thousands of objects larger than 100 kilometers in diameter and possibly trillions of smaller bodies. It is the source of many of the short-period comets that occasionally visit the inner solar system, comets with orbital periods less than 200 years, whose orbits are confined to relatively near the plane of the solar system. Like the asteroid belt, the Kuiper Belt is not a region of closely packed debris. It is an enormous volume of space in which objects are scattered thinly but distributed in vast numbers. The average distance between Kuiper Belt objects is still millions of kilometers. A spacecraft traveling through the Kuiper Belt would pass through it without encountering anything, as New Horizons did without incident on its way to Pluto. The Kuiper Belt exists because of Neptune. Beyond Neptune's orbit, the density of material in the early solar system was too low, and Neptune's gravitational influence too disruptive for material to gather into a planet. What we see here is the remnant of the outer solar system's formation, objects that couldn't come together, preserved in the cold at distances they have occupied for billions of years. The temperatures here are approximately negative 220 degrees Celsius. Chemical processes are essentially frozen. What formed in the Kuiper Belt has remained essentially unchanged since the solar system was young. The most famous Kuiper Belt object, by a considerable margin, is Pluto. Pluto was discovered in 1930 by a 23-year-old astronomer named Clyde Tombaugh at the Lowell Observatory in Flagstaff, Arizona. He was systematically comparing photographic plates of the night sky, looking for a predicted ninth planet. On February 18, 1930, he identified a small moving dot in the constellation Gemini. It was Pluto. For 76 years, Pluto was the ninth planet. Children memorized it in the planetary sequence. It appeared in every diagram of the solar system. In 2006, the International Astronomical Union formally defined what a planet is for the first time. The definition required three things. A body must orbit the Sun, must have sufficient mass for its self-gravity to make it roughly spherical, and must have cleared the neighbourhood around its orbit of other debris. Pluto meets the first two criteria. It does not meet the third. Its orbit sits within the Kuiper belt, populated by hundreds of thousands of similar objects. Pluto was reclassified as a dwarf planet, which in some ways is the more precise description. It is the largest known member of a vast family of objects, not a dominant body clearing its path. What ended the cultural argument, in a sense, was not the reclassification, but what happened in 2015. On July 14th, 2015, NASA's New Horizons spacecraft completed a flyby of Pluto after a 9.5-year journey. It was traveling so fast, approximately 14 kilometers per second, that it could not slow down and enter orbit. It had one chance: a single flyby in which every instrument gathered as much data as possible in the hours of closest approach, and then the spacecraft continued outward. The images that came back changed our understanding of Pluto entirely. Pluto is not a dead, inert ball of ice and rock. It is complex. It is active. It is extraordinary. The most striking feature visible in the first clear images is a vast, heart-shaped region near the equator. The left side of the heart, an enormous plain of nitrogen ice approximately 1,000 kilometers across, was named Tombor Regio in honor of its discoverer. It is geologically young. The surface shows no impact craters, indicating it has been resurfaced relatively recently by the slow glacial flow of nitrogen ice. Pluto, this small world so far from the Sun, has enough internal energy to drive geological processes. The mountains visible at the edges of Tombor Regio rise up to approximately 3,500 meters, comparable to the European Alps. They are made of water ice, which at Pluto's temperatures is as hard as rock. They are geologically young as well, estimated at no more than 100 million years old, recent on solar system timescales. Pluto has an atmosphere. It is thin, surface pressure approximately 10 microbars, about 100,000 times thinner than Earth's, but it is there. It is primarily nitrogen with methane and carbon monoxide. Some of this atmosphere freezes onto the surface when Pluto is at its furthest from the Sun, then sublimates back into gas when Pluto is closer. Pluto's orbit is highly elliptical, ranging from 29.7 astronomical units at perihelion to 49.3 astronomical units at aphelion, and this variation creates seasons on an extreme scale. When Pluto reaches its furthest point, which won't happen for over 200 years, its atmosphere may largely collapse, freezing entirely to the surface. Pluto has 5 moons. The largest, Charon, has a diameter about half that of Pluto itself. The two do not orbit a common center within Pluto, they orbit a point in space between them. They are technically a double dwarf planet system. Charon and Pluto are tidally locked to each other, always presenting the same face. From any point on Pluto facing Charon, the moon would appear completely motionless in the sky. Charon's poles are red. The current hypothesis is that nitrogen and methane escaping from Pluto's atmosphere drift over to Charon, are processed by ultraviolet radiation and cosmic rays into complex organic compounds, tholins, and accumulate near the poles. Charon is being slowly painted red by chemistry, drifting across from its companion. New Horizons did not stop at Pluto. On January 1, 2019, it made a flyby of an object in the Kuiper belt called Arrokoth, a name from the Powhatan language meaning sky. Arakoth is a contact binary, two roughly spherical lobes that came together extremely slowly, touching gently and merging. It looks like a red snowman. At 44 astronomical units, Arakoth is the most distant object ever observed at close range by any spacecraft. Its red color comes from tholins. Its shape and the very gentle way the two lobes came together tells us something important about how planetesimals formed in the early solar system. Not through violent collisions, but through slow, patient accumulation, growing gradually from the drifting material of the early solar disk. Pluto and the Kuiper Belt remind us that the solar system is not an archive. Processes continue out here, slow, cold, ancient, but real. The outer solar system is not static. It is a working system that has been running quietly for 4.5 billion years. Beyond the Kuiper Belt, at distances from roughly 50 astronomical units outward to several hundred astronomical units, lies a region called the scattered disk. The scattered disk is less well defined than the Kuiper Belt. It is a population of objects whose orbits have been perturbed, gravitationally scattered, most likely by Neptune during a period of planetary migration in the early solar system. Shortly after the solar system formed, the giant planets were not where they are today. The leading model of early solar system evolution proposes that Jupiter, Saturn, Uranus, and Neptune formed in different positions and then migrated over hundreds of millions of years, driven by interactions with the disk of material surrounding the young sun. As they migrated, their gravitational influence scattered enormous numbers of small bodies outward into the scattered disk and beyond, and inward to crash into the terrestrial planets. The period of intense cratering we noted on Mercury, the late heavy bombardment, is believed to be a direct consequence of this planetary migration. The scars we see on ancient surfaces across the inner solar system are the record of that chaotic era. The scattered disk is the source of long-period comets, comets with orbital periods greater than 200 years, arriving from almost any direction of the sky. The most significant known body in the scattered disk is Eris. Discovered in 2005 by Mike Brown and his team at Caltech, Eris sits in an orbit that carries it from approximately 38 astronomical units at its closest approach to approximately 97 astronomical units at its furthest. It takes 559 years to complete one orbit. For most of those 559 years, it is more than 3 times further from the Sun than Pluto. Eris has an approximate diameter of 2,326 kilometers, very slightly smaller than Pluto as measured precisely, but slightly more massive. It is the most massive known dwarf planet. Its surface is one of the most reflective in the solar system, reflecting approximately 96% of the sunlight that hits it. Most likely a fresh methane frost deposited when Eris was near its closest approach to the Sun, and a small amount of surface ice sublimated, then fell back across the entire surface as it moved away. It was the discovery of Eris that forced the International Astronomical Union to define what a planet is. If Eris counted as a planet, dozens more similar objects might also qualify. The solution, reclassify Pluto as a dwarf planet and welcome Eris to the same category, was logical. It was also for people who had spent a lifetime thinking of Pluto as the 9th planet, an adjustment. In November 2003, while conducting the same survey that would eventually find Eris, Mike Brown and his colleagues discovered an object that didn't fit any existing category. They called it Sedna, after the Inuit goddess of the sea. Sedna's orbit carries it between approximately 76 astronomical units at its closest approach to the Sun and approximately 937 astronomical units at its furthest. It takes approximately 11,400 years to complete one orbit. When Sedna was discovered, it happened to be near its perihelion, its closest approach. For most of those 11,400 years, Sedna is more than 900 astronomical units away, more than 7 times further from the Sun than the heliopause. At 76 astronomical units, even at its closest, Sedna is well beyond the Kuiper belt. And the more significant problem is that its perihelion is too far from Neptune for Neptune's gravity to have scattered it into its current orbit. Whatever put Sedna where it is, it wasn't Neptune. Several explanations have been proposed. A star passing close to our solar system in its early history could have tugged objects into distant, eccentric orbits. The Sun may have formed in a dense stellar cluster, and the collective gravity of many nearby stars during that cluster phase may have shaped the outer solar system's architecture. Or there may be another large planet in the far outer solar system, a body massive enough to gravitationally shepherd objects like Sedna into their unusual orbits. This hypothetical object has been called Planet 9. The evidence for it is indirect. Several objects in the extreme outer solar system, including Sedna, have orbits that appear to cluster in a way that is statistically unlikely to be random. The orbits look as though they have been influenced by the gravity of something large, something with perhaps 5 to 10 times the mass of Earth in a highly elliptical orbit that carries it to distances of perhaps several hundred astronomical units. Planet 9 has not been found. Many surveys have searched appropriate regions of sky and found nothing. It may not exist. The clustering may be a product of observational bias rather than a real gravitational influence. But the hypothesis remains active and is being seriously pursued. The Vera Rubin Observatory in Chile, beginning full science operations in the mid-2020s, is expected to discover an enormous number of new outer solar system objects. If Planet 9 exists and is detectable by survey observations, the Vera Rubin Observatory has a reasonable chance of finding it. Sedna itself is red, one of the reddest objects in the solar system. Its color comes from billions of years of radiation processing, slowly converting surface ices to tholins. It has no known moons. No spacecraft has visited it. We know almost nothing about it beyond its orbit, its approximate size of 995 kilometers, its color, and its extraordinary path through the outer solar system. As we travel outward through the scattered disk and beyond, we are also traveling through a structure that has enclosed us since the start of our journey, the heliosphere. The heliosphere is the bubble of space dominated by the Sun's solar wind. The solar wind is a continuous stream of charged particles, primarily protons and electrons, flowing outward from the Sun in all directions at speeds between roughly 300 and 800 kilometers per second. It is not wind in any sense you experience on Earth. It is a plasma, an ionized gas, flowing outward continuously as long as the Sun burns. This solar wind inflates a bubble around the Sun, the heliosphere, and everything inside that bubble is, in a physical sense, inside the Sun's extended atmosphere. The solar wind does several important things. It is responsible for comet tails, the ion tails that always point directly away from the sun, regardless of which direction the comet travels, because the solar wind physically pushes them. It is responsible for auroras on Earth and other planets. And it maintains the boundary of the heliosphere against the interstellar medium, the sparse material that exists between stars throughout the galaxy. At approximately 80 to 100 astronomical units from the Sun, the solar wind decelerates abruptly, dropping from supersonic to subsonic speeds. This boundary is called the termination shock. Voyager 1 crossed the termination shock in 2004, Voyager 2 crossed it in 2007. Beyond the termination shock lies the heliosheath, a turbulent region where the slowed solar wind interacts with the interstellar medium, compressed and heated, forming a boundary layer between the Sun's domain and everything else. The outer edge of the heliosheath is the heliopause. It sits at approximately 120 to 125 astronomical units. This is where the solar wind effectively ends, where its pressure can no longer push back against the interstellar medium. Beyond this line, the Sun's charged particles can no longer dominate. The interstellar medium takes over. Voyager 1 crossed the heliopause on August 25, 2012. The confirmation came from an unexpected event. A large solar eruption sent a wave of energy outward through the heliosphere. When this wave reached Voyager, more than a year later, it caused the surrounding plasma to oscillate at a measurable frequency, a frequency directly related to plasma density. The density Voyager 1 measured was approximately 40 times greater than inside the heliosphere. That confirmed it. The spacecraft was in the interstellar medium. Voyager 2 crossed the heliopause on November 5, 2018. You are now at 120 astronomical units, having crossed the last active boundary of the Sun's influence. The solar wind is no longer around you. What surrounds you now is the interstellar medium, the thin, ancient plasma that fills the space between stars throughout the galaxy. But the solar system, defined not by the solar wind but by gravity, continues much further. There are two objects made by human hands that are further from Earth than anything else we have ever built. They are called Voyager 1 and Voyager 2. They were launched in 1977 within weeks of each other. Their mission was designed to take advantage of a rare alignment of the outer planets, a configuration that occurs once every 175 years that would allow a single spacecraft to use each planet's gravity to accelerate toward the next in a technique called a gravity assist. Voyager 1 launched on September 5, 1977. Despite launching after Voyager 2, it followed a faster trajectory and has always been the further of the two. It flew past Jupiter in March 1979, gathering close-up images of the Galilean moons, including the first photographs of Io's active volcanoes. It flew past Saturn in November 1980, making a targeted flyby of Titan. At Saturn, Voyager 1's trajectory was deliberately bent southward, away from the plane of the solar system, and it has been traveling in that direction ever since. Voyager 2 launched on August 20th, 1977. It flew past Jupiter in July 1979, Saturn in August 1981, Uranus in January 1986, and Neptune in August 1989. Voyager 2 is the only spacecraft in history to have visited all 4 outer planets. At Neptune, its trajectory was also bent out of the plane of the solar system, in a different direction from Voyager 1. Both spacecraft were designed to last until 1990. They are still operating. As of mid-2025, Voyager 1 is approximately 163 astronomical units from the Sun, moving at roughly 17 kilometers per second. The radio signal from Voyager 1, traveling at the speed of light, takes approximately 22.5 hours to reach Earth. When engineers at NASA's Jet Propulsion Laboratory send a command to Voyager 1, they wait more than 22 hours for it to arrive. When data comes back, they are receiving information about where Voyager 1 was 22 hours ago. The team that manages the Voyager missions has operated these spacecraft for nearly half a century. They have managed the power budget with extraordinary care, turning off instruments one by one as the radioactive thermal generators have slowly declined. Both spacecraft are expected to maintain at least some operational capacity until approximately 2025 to 2030. After which they will fall silent. But they will not stop. They will continue traveling unpowered through the interstellar medium for longer than human civilization has existed. In approximately 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445. In approximately 296,000 years, Voyager 2 will pass within 4.3 light-years of Sirius, the brightest star in Earth's night sky. Each Voyager carries a golden record, a 12-inch gold-plated copper disc containing 116 images, greetings in 55 languages, and 90 minutes of music from across human cultures. Bach, Beethoven, Chuck Berry, a Navajo night chant, a pygmy girl's initiation song, music from Japan, Azerbaijan, Peru, Senegal, and a dozen other places. It contains sounds, wind, rain, surf, thunder, a train, a Saturn V rocket, a mother's first words to her newborn child. The golden records were the idea of Carl Sagan. He described them as a message in a bottle cast into the cosmic ocean. The probability that they will ever be found by anyone is essentially zero. In the empty vastness of interstellar space, the chances of any object encountering another are vanishingly small. The records were created knowing this. They were created anyway. As much as anything, they are a portrait of what it meant to be human at a particular moment in history, sent out into a universe that may never read them. There is something worth sitting with in that. We took the trouble, knowing the odds, to include Chuck Berry alongside Bach, to include the sound of a child's first cry alongside mathematical diagrams. We decided those things were worth saying, worth sending, worth putting into the dark. The Voyager program has been called the greatest voyage of exploration in human history. It is not an unreasonable claim. We are at 120 astronomical units. The heliopause is behind us. Interstellar space surrounds us. But the solar system has one more structure, one that we have never seen directly, never visited, never confirmed by any observation. And yet its existence is accepted with near universal confidence among astronomers. The Oort cloud, named after Dutch astronomer Jan Hendrik Oort, who proposed its existence in 1950, the Oort cloud is inferred from the long-period comets that occasionally fall into the inner solar system. These comets, with orbital periods of hundreds, thousands, sometimes millions of years, arrive from almost every direction of the sky. Their orbits, when traced backward, suggest they originate from an enormous, roughly spherical shell of material at distances far beyond the known planets. Oort proposed that this shell contains trillions of icy bodies, remnants of the solar system's formation, sitting frozen in the dark at the very edge of the sun's gravitational reach. Occasionally, a gravitational disturbance, a passing star, the gravitational tide of the galaxy itself, a large object drifting nearby, nudges one of those bodies slightly. Its orbit changes. It begins to fall slowly toward the inner solar system. Over thousands or tens of thousands of years, it falls inward. Eventually it approaches the sun, its surface ices begin to sublimate, it develops a tail, and we observe it as a long-period comet blazing briefly across our night sky. Then it swings around the sun and heads back outward, back into the dark, back toward the Oort cloud, from which it came. The Oort cloud is believed to have two distinct regions. The inner Oort cloud, sometimes called the Hills cloud, is a flattened, disc-like structure extending from roughly 2,000 to 20,000 astronomical units. The outer Oort cloud is a roughly spherical shell extending from about 20,000 astronomical units to perhaps 100,000 astronomical units. At 100,000 astronomical units, you are halfway to the nearest star. The outer boundary of the Oort cloud, where the sun's gravity finally yields to the combined gravitational pull of the rest of the Milky Way, is often considered the true edge of the solar system. It is an appropriate boundary. It is where the sun's story ends and the galaxy's begins. No object in the Oort cloud has ever been directly observed. No telescope has ever detected an Oort cloud body while it was actually in the Oort cloud. The evidence for its existence comes entirely from the comets it sends inward and from the mathematical consistency between those observed orbits and a reservoir of material at the distances Oort proposed. The inference is solid. The confidence is high. The structure itself remains invisible if you were somehow suspended in the outer Oort cloud at perhaps 50,000 astronomical units halfway through it. What would you see? The sun would be a star, the brightest star in the sky by a wide margin, clearly distinguishable, clearly the dominant light source, but not a disk, not the sun as you know it. Just the brightest star. The planets would be invisible to the naked eye, lost in the glare of the sun, or too dim to detect. The familiar constellations of Earth's sky would still be largely recognizable. You have not moved far enough from Earth to significantly shift the apparent positions of the nearby stars. The Milky Way would spread across the sky as a broad band of light. It would look, in many ways, like an extraordinarily clear night sky from a very dark location on Earth. The difference would be the cold. At 50,000 astronomical units, the temperature of any object in equilibrium with the radiation environment would be approximately negative 268 degrees Celsius, a fraction of a degree above absolute zero. This is the temperature of the cometary bodies stored there, frozen hard, dark, red-tinted by tholins ancient beyond imagination. Objects that have been sitting in the dark since the solar system formed. The Oort cloud is not static. The galactic tide, the differential gravitational pull of the mass of the Milky Way on objects at different distances from the galactic center, gently stirs its contents over millions of years. Stars passing through the outer regions of the galaxy periodically come close enough to gravitationally perturb the outer Oort cloud, shaking objects into new orbits and sending some of them inward. This is the continuous mechanism that replenishes the supply of long-period comets arriving in the inner solar system. The comets we see, those ancient, dusty, icy visitors, have been waiting in deep freeze at the edge of the solar system for perhaps 4.5 billion years. Some of them set out on their inward journey nudged by a passing star millions of years ago. They have been travelling ever since in the dark at speeds too slow to perceive, on trajectories so long that the journey itself is older than our species. A comet blazing through the inner solar system past the warming sun, developing its bright tail. That comet may have set out from the Oort cloud before the first modern humans walked in Africa. There is no single edge of the solar system. There are several boundaries, each marking a different kind of limit. The innermost is the termination shock, at roughly 80 to 100 astronomical units, where the solar wind transitions from supersonic to subsonic. Beyond it, the heliosheath. Beyond that, the heliopause at approximately 120 astronomical units, where the solar wind ends and the interstellar medium begins. This is the edge of the Sun's active wind domain. Voyager 1 crossed it in 2012, but gravity extends much further. Sedna, at perihelia of 76 astronomical units and aphelion of 937 astronomical units, is gravitationally bound to the Sun. Everything in the Oort cloud, trillions of objects, is gravitationally bound to the Sun. The gravitational edge of the solar system, the point beyond which an object is more influenced by the galaxy than by the Sun, lies at roughly 100,000 to 125,000 astronomical units. So the answer to where does the solar system end depends on what you mean by the solar system. If you mean the region where the Sun's breath reaches, the heliosphere, the answer is 120 astronomical units, and Voyager 1 has crossed it. If you mean the region where the Sun's gravity dominates, the full extent of solar gravitational influence, the answer is roughly 100,000 astronomical units, and no spacecraft we have built, or could build with current technology, will reach it within any time frame that has human meaning. Between the outer Oort cloud and the nearest star lies the true void. Beyond 100,000 astronomical units, the Sun's gravitational story ends. What fills that space, the gap between our solar system and Alpha Centauri, is the interstellar medium. Thin, cold, ancient plasma, magnetic field lines, cosmic rays, the faint warmth of the cosmic microwave background. No objects of any significant size, no rocks, no ice, no collected structure, just the space between. Alpha Centauri consists of 3 stars. Alpha Centauri A and B are a binary pair, 2 stars orbiting each other at a separation roughly comparable to the distance between the Sun and Uranus. They sit 4.37 light-years from Earth, approximately 276,000 astronomical units. The third member, Proxima Centauri, is a small red dwarf orbiting the binary pair at an enormous distance. At 4.24 light-years, 268,000 astronomical units, Proxima Centauri is the closest star to our Sun, and it has planets. In 2016, a planet was confirmed in Proxima Centauri's habitable zone, the range of distances where liquid water could theoretically exist on a planetary surface. The planet, Proxima Centauri b, orbits its star every 11.2 days and has a mass slightly greater than Earth's. Whether it has an atmosphere, whether it has liquid water, whether it has any conditions that could support life, is not known. Proxima Centauri is an active flare star emitting regular bursts of intense radiation that could strip an unprotected atmosphere. The habitability of Proxima b is genuinely uncertain. To travel from the outer Oort cloud to Proxima Centauri at Voyager, one's current speed would take approximately 74,000 years. That is from the edge of our solar system, not from Earth. At 10% of the speed of light, a speed no current or near-future technology can achieve, the journey from Earth would take approximately 43 years. At 20% of the speed of light, the concept explored by the Breakthrough Starshot initiative, it could take about 20 years. Breakthrough Starshot proposes sending gram-scale spacecraft, essentially microchips with light sails, accelerated by powerful Earth-based lasers, to the Alpha Centauri system. The physics is not ruled out. The engineering challenges are formidable, but the ambition is serious and the science behind it is real. If such a spacecraft reached Proxima b and successfully transmitted data back, the signal would take 4.24 years to arrive. We would receive in real time information about the surface of another star's planet. We would know something about what is there, whether what is there is simply rock and ice, or chemistry of some complexity, or something with no category in our current vocabulary. We do not know, but we are closer, technically and conceptually, to being able to ask the question directly than at any previous point in human history. The tools are being built, the missions are being planned. The question is taking on a new seriousness. You have traveled from the surface of the Earth, standing on solid ground under the familiar sun, to the outer edge of everything the sun holds. You passed through the rocky inner planets, each with its own character, its own surprises. Through the asteroid belt, not the dense corridor of science fiction, but the vast, almost empty archive of a planet that never formed. Past Jupiter, sovereign of the outer solar system, host to a moon that may be the most important piece of real estate in the solar neighbourhood. Past Saturn, with its improbable rings and its methane-seasoned moon, and its geysers of liquid water erupting from the south pole of Enceladus. Past Uranus, lying on its side for reasons that no one fully understands, with a cliff tall enough to require 12 minutes to fall. Past Neptune, with its impossible winds and its captured moon slowly spiraling to its fate. Through the Kuiper Belt, where Pluto turned out to be not a small, frozen, inert ball, but a geologically active world with mountains and glaciers and weather, and a companion almost as large as itself. Through the scattered disk, where Eris and Sedna occupy orbits that hint at histories we haven't fully reconstructed. Through the heliopause, where the sun's breath finally gave out and the interstellar medium began. Out to the theoretical edge of the Oort cloud, where trillions of objects wait in the cold, and where the sun's gravity finally yields to the pull of the galaxy. And in the space between the outer Oort cloud and the nearest star, almost nothing. The void between. The gulf that puts all the distances we have covered in some perspective. Everything we have visited tonight is inside one small star's gravitational neighbourhood, one star among 300 billion in this galaxy alone. There are things we know about this region that we didn't know 10 years ago. New Horizons showed us Pluto's heart. Cassini revealed Enceladus's geysers. The Voyagers measured the interstellar medium from inside it. The James Webb Telescope showed us Neptune's rings in new clarity. A ground survey in Chile found a black hole in our own stellar neighbourhood. The discoveries keep accumulating, not because space has changed, but because our ability to look at it keeps improving. There are things we still don't know. whether Titan's methane chemistry gives rise to any organized complexity, whether Europa's ocean contains anything that swims, whether Planet 9 exists, and if so, what it means for our understanding of how the solar system formed, what the outer Oort cloud actually looks like from close range, a thing we may not know within any of our lifetimes. What we do know is the scale of the place we live in, not as an abstract number, but as something you have traveled through tonight, step by step, world by world, boundary by boundary. The solar system is not a small neighbourhood, it is enormous, and it is ours, or we are its, which may be the more accurate way to say it. A comet that last passed through the inner solar system at the time of the Roman Empire is on its way back now, outward, past Neptune, past the Kuiper Belt, into the scattered disk, falling back toward the Oort cloud from which it came. It will not return for thousands of years. While it is out there in the dark, everything that matters to us on Earth will happen. All the history yet to be written, and the comet will be out there, slowly arcing back toward Aphelion, indifferent, ancient, perfectly ordinary by the standards of the outer solar system. That is the scale of the place. Sleep well.